Hey guys, so in this video we are going to discuss vertical curves. Now, before our semester was so unceremoniously ended, we've already tackled and discussed horizontal curves. It is only fitting, of course, to continue with vertical curves. But before we continue, let us first review what a horizontal curve is used for. Now, if you can recall, a horizontal curve is used to facilitate turning. So therefore, you create some sort of easement. You make it easier for the vehicle to turn. In that regard, we can also treat vertical curves as some sort of easement, but we no longer use it for turning. Rather, from the name vertical, we use it for easement in a vertical plane. Now, interchangeably, vertical curves are also called parabolic curves. Why parabolic curves? Now, in horizontal curve, recall that we used arcs, circular arcs. We call them simple curves. Put two of them together, then you have a compound curve or a reversed curve. So for a vertical curve, we are now going to use a parabola. Alright? So let me illustrate how we're going to use a parabola to create an easement for vehicles in the vertical plane. So say for example, I have a road that goes this way, and I have another that goes, say, that way. If we consider a vehicle going from this point up to that point and then going there, it would of course constitute some sort of discomfort, not just for the driver but also for his passenger, to traverse this kind of road if it is very steep, considering that no change in slope, no change in slope, no change in slope, an abrupt change not only in the value of the slope but also in the orientation. So for vertical curves, the first element that we are going to study is what we call the grade. The grade is just another term for the slope, meaning for these two roads, each of them has their own grade. That means that this road here will have a grade, say, G1, and this road will also have a grade, say, G2. Now, grade is given in percent form, or it is a percentage. Now remember, again, let me reiterate, grade is just another term for the slope. So, if you have these two roads, how then do we fit our parabola or the parabolic curve between these 2 points? Now, before I put the parabola here, there are actually two kinds of parabolic curves that we could study, but we're only going to concentrate on this video on one kind. So, the two kinds is symmetrical and asymmetrical parabolic curve. Now, for simplicity's sake, of course, we're going to discuss first in this video symmetrical curves. So, say for example that I want to start my curve right here. Of course, this is where those two roads intersect, and let us say for example that your road ends right there. Your curve now is going to be that one. So notice that it is tangent, this curve is tangent to this line, and it is also tangent to that line. Now, if we can recall from your calculus, the parabola is a polynomial in the second degree, which means that if we take the derivative of that, we get a first degree polynomial, or a first degree equation, which again means that the first derivative of a curve is actually its slope. We now know that the change in slope from here to there is actually linear. So we have a not an abrupt change, not in just the value of the slope and the orientation, but a gradual change in slope, a linear 1. Now, if we are going to plot that, let's plot it. Oops. Let's use a white pencil for that. If we're going to plot that, say for example right there. Now, say for example, you have your, for this is the plot, take note, this one, this area right here, we are trying to plot the change in slope. So we are plotting the slope, the values of the slope of your parabola. So at this point, this is G1, and of course, here, you will have G2. And you will notice, why is it below our line? Why is it below this line? Now take note, if we review from your algebra again, that this line has a positive slope while this line has a negative slope. And so, here you are. So if you are going to connect, take note, we've already determined from our calculus that the change in slope is linear. We can just say that that is where your line goes, and we can just shade it just for clarity. And I forgot to write here, this is, oops, this is G2. Alright, so that's your grade. Now, the next element that we are going to look at is the length of the curve. Now, from your fundamentals of surveying, we know that when we talk about length or distances or horizontal distances, we do not take into consideration the change in elevation in our surface. So that means then that we do not measure length along that curve. Rather, we measure it along this one, the horizontal plane, and that is the length of your curve. Now, because we are also considering a symmetrical parabolic curve, if I'm going to draw a vertical line down there, then we can say that this is L over 2 or 0.5 L, whichever you like. Alright? So that's its length. Next, we need to consider where the highest point of the curve is. Now, if we want to determine where the highest point of the curve is, you must remember from your calculus that when you take the first derivative and you get the slope, where the slope is 0 is where your maximum or minimum value occurs. So from our graph down here, we see that 0 slope occurs there. So if I'm going to draw a vertical line just so we can find where that is, we can find it. Oops. Let's use a thinner line for that. And that is where your apex occurs. Notice that it is slightly off the middle. The only way for the middle of this line, and this line, for those two lines to coincide, G1 and G2 must be equal. But if we are going to assume for our example right now that G1 and G2 have different values, then this must occur. Now take note that this one is your apex or the highest point on the curve. Alright? So that is where it occurs. Now, if we now have to locate where that happens. So we can put here a dimension and another dimension right here, which we will call S1 and S2. So if we want to measure our apex or the distance of the apex from the starting point of our curve to the last point of our curve, then we will use S1 and S2. So if we use ratio and proportion, it is actually easy for us to determine what the value of S1 and S2 is, take note that you have values for G1 and G2 right there. And so we will have, quite simply, S1 is given by G1 times the length of the curve over G1 minus G2, and consequently S sub 2 must be equal to G sub 2 L over G1 minus G2. Now take note, now for this formula to work, these formulas to work, we need to consider the algebraic signs of your grade, meaning that this has a positive sign and that one has a negative sign. Alright? So, we've already considered your grade, your length, and the distances of the apex from the starting point to the last point of your curve. Now take note, from your horizontal curve, where your curve starts is called the PC, where the curve ends is called PT, and where the tangent lines meet is PI. So in the parabolic curve, in vertical curves, it's the same. So we can just write this point therefore is PC, this point here is PI, and this point right here is PT. Meaning we can now say that S1 is the distance of the apex from PC, the point of curvature, and S2 is the distance of the apex from PT, the point of tangency. So what else? What other elements can we get from here? Another element is the distance from PI to the curve. Now, in your horizontal curve, we call this the external distance. In parabolic curves, we just use the value h. So, h has a formula of L over 8 G1 minus G2. Alright? And lastly, we can have, take note, if you would look at it, that this is a straight line, it must have a slope. Now, because it has a slope, we can solve it. Remember, slope is just rise over run. The slope of this graph that represents the change in the grade, R is given by G1 minus G2 over L. Now, R is what we call the rate of change of grade. So next, what if we want to determine the elevation at the apex? Or for that matter, the elevation on other parts or on arbitrary parts of the curve. We have to go to our next page here and allow me to redraw our parabolic curve here. I'm going to make it slightly bigger so that we can actually draw a more accurate representation for this. Alright, so that's our representation. I just redrew what's on the other page. So what if I want to find the elevation of an arbitrary point? Say for example, that point there, we will call that point A. Take note that this is still PC. Now in order for me to solve for the elevation at A, given that I already know what the elevation at the point of curvature is, I need to locate point A first. So to locate it, I must first find the horizontal distance from PC to A. So let's say for example that I already know how far it is from PC. We will call that value, say, x. Now, according to Euclid, you can also locate a point by measuring a vertical line coming from the tangent on the parabola. What that means is that therefore I can create a distance here, a vertical distance coming from the tangent to your parabola. We will call this distance y. Now, as I have said also, maybe dozens of times, that in order for us to solve geometric figures in engineering, we need to create triangles. So the triangle that is most obvious there to create is, of course, this one. Let's just continue this line and that line, and you will have this triangle right here. Now, I will call the distance coming from PC to this point right here where our vertical and horizontal line meet, I will call that small letter h. Notice now that I can solve for the elevation at point A. How do I do that? If I already know the elevation at PC, I'm just going to add the value of h. If I can solve the value of h, take note this is a horizontal line, no change in elevation, and then I can just subtract the value of y and I will get the elevation at A. So first, we need to solve for the value of h and y. So to solve for the value of h, we can just write that your slope, take note, g1, take note that this line, this one, has a slope of g1. Now g1, take note, the slope is just rise over run. So you will have rise and run. And consequently, the values for that, this must be equal to h over x. Or therefore, I can rewrite h is just g1 times x. Solved for h. How about y? For y, we need to take what we call, or we need to use what we call the squared property of parabola. So the squared property of parabola would look like this. You will have y over x squared. Take note again that we are measuring from PC through the tangent line. So this must be equal to, if you look at it, y is the distance from your tangent line to your parabola. So another point on the parabola is right here. So from the tangent line to the parabola, this must be equal to h over, take note, x is the distance from PC to the point, and so this must be the distance from PC to PI. So you will have, this is going to be L over 2 squared. Or I can just write that your y is equal to 4hx squared over L squared. So now I can solve. I can just divide my screen right here, and I can say that y is equal to, what is h? H from the previous screen was L over 8 G1 minus G2. So this is times 4x squared over L squared. We can cancel that, cancel that, cancel that, cancel that, and make this 2. And you will have y is equal to, and I'm going to rearrange just so you can see, G1 minus G2 over L times x squared over 2. But what is this? That's the formula for the rate in change in grade. So that means that I can just write here y must be equal to r x squared over 2. So now, you have two values for h and y. Meaning that I can now solve for the elevation at A or for any other point. Now, take note, if we will review, how do we solve for the elevation at A? We take PC, we add h, we subtract y. So, in equation form, of course, that would look like the elevation at any point A. This must be equal to the elevation at PC plus h minus y. If we are going to substitute the equations that we've derived for h and y, we will have elevation at A is equal to elevation at PC plus g1 times x minus rx squared over 2. This equation is our general equation for finding elevation at whatever point on the parabolic curve. If you want to find, for example, what is the elevation at the apex? So the elevation at the apex, you can solve by substituting x to s1. Or the other way around, substituting s1 to x. So those are all the elements that we can study for the parabolic curve. What's left for us to do is to solve practice problem so that we can familiarize ourselves with how to use all these formulas that we have discussed, all these elements that we have discussed. We still also have to discuss asymmetrical curves, and we also have what we call sag curves, because as you notice, not all vertical curves must be going this way, or this is what we call the summit curve. A vertical curve could also go like this, which we will call the sag curve. Now, all the elements remain the same. It's just that we have a different value now for G1 and G2. Whereas for summit curve, you have a positive G1 and a negative G2. For sag curve, you now have a negative G1 and a positive G2. So, alright, that's it. I will see you on the next video for practice problems. Bye!